To determine the capacitive reactance of a 26.5 microfarad capacitor in a 400 Hz AC circuit, firstly, you need to convert microfarads to farads. 1 microfarad is equal to 10 to the power of negative 6 farads. Therefore, 26.5 microfarads is equal to 26.5 multiplied by 10 to the power of negative 6 farads. Secondly, calculate the capacitive reactance using the formula Xc equals 1 divided by 2 times pi times F times C, where Xc is the capacitive reactance in ohms, F is the frequency in Hertz, and C is the capacitance in farads. Substituting the given values into the formula, Xc equals 1 divided by 2 times pi times 400 Hz times 26.5 times 10 to the power of negative 6 farads. This simplifies to Xc equals 1 divided by 530.5 times 10 to the power of negative 6. Finally, this results in Xc equals 1882 ohms. Therefore, the capacitive reactance of the 26.5 microfarad capacitor in a 400 Hz AC circuit is 1882 ohms. The capacitive reactance is the opposition to the flow of alternating current, AC, caused by a capacitor. Capacitors store electrical energy in an electric field, and this storage mechanism impedes the flow of AC, leading to capacitive reactance. The capacitive reactance is measured in ohms and is inversely proportional to both the frequency of the AC signal and the capacitance of the capacitor. The formula Xc equals 1 divided by 2 times pi times F times C mathematically expresses this relationship. A higher frequency or a larger capacitance will result in a lower capacitive reactance, meaning the capacitor offers less opposition to the AC flow. Conversely, a lower frequency or a smaller capacitance will result in a higher capacitive reactance, indicating greater opposition to the AC flow. In the context of a 400 Hz AC circuit, which is a frequency higher than the standard 50 or 60 Hz used in household power, the capacitive reactance will be lower compared to the same capacitor used in a lower frequency circuit. This is because the capacitor has less time to charge and discharge during each cycle of the AC signal, effectively reducing its opposition to the current flow. The 26.5 microfarad capacitor represents the capacitance value. Capacitance is the ability of a capacitor to store electrical charge. A microfarad is a unit of capacitance, specifically 1/1,000,000 of a farad. The farad is a standard unit of capacitance in the International System of Units. Understanding the conversion between microfarads and farads is crucial for accurate calculations. Using scientific notation, 26.5 microfarads is expressed as 26.5 times 10 to the power of negative 6 farads, which is equivalent to 0.265 farads. The term 2 times pi in the formula represents the angular frequency, denoted by the symbol omega. Angular frequency is the rate of change of the phase angle of a sinusoidal waveform. It is related to the frequency f by the equation omega equals 2 times pi times f. In the calculation, using 2 times pi times 400 Hz gives approximately 2513.27 radians per second, which is the annular frequency of the AC signal. The calculation Xc equals 1 divided by 2 times pi times F times C involves several steps. Firstly, calculate the product of 2 times pi times F times C, which represents the annular frequency multiplied by the capacitance. This value is approximately 0.5305. Secondly, divide 1 by this product to obtain the capacitive reactance in ohms. The result is approximately 1882 ohms, which is the opposition to the AC flow offered by the 26.5 microfarad capacitor at 400 Hz. This value is significant for circuit design and analysis. When designing circuits operating at higher frequencies, such as 400 Hz, the capacitive reactance of components becomes more critical. Capacitors are used in various applications, including filtering, energy storage, and signal coupling. Understanding how the capacitive reactance changes with frequency is essential for selecting appropriate capacitor values to achieve desired circuit performance. For example, in a filtering application, a capacitor may be used to block low-frequency signals while allowing high-frequency signals to pass. The capacitive reactance of the capacitor determines the cutoff frequency of the filter. Similarly, in an energy storage application, the capacitance value determines the amount of energy that can be stored. The capacitive reactance affects the charging and discharging time of the capacitor. In signal coupling applications, capacitors are used to block DC signals while allowing AC signals to pass. The capacitive reactance ensures that the AC signal is not attenuated excessively. The value of 1882 ohms represents the impedance offered by the capacitor at 400 Hz. Impedance is the total opposition to current flow in an AC circuit, including both resistance and reactance. In a purely capacitive circuit, the impedance is equal to the capacitive reactance. However, in a circuit containing both resistance and capacitance, the impedance is a complex quantity that includes both the resistive and reactive components. The impedance is calculated using the formula Z equals the square root of R squared plus XC squared, where Z is the impedance, R is the resistance, and XC is the capacitive reactance. Understanding impedance is crucial for analyzing AC circuits and predicting circuit behavior. The concept of capacitive reactance is closely related to the concept of inductive reactance. Inductive reactance is the opposition to the flow of AC caused by an inductor. Inductors store energy in a magnetic field, and this storage mechanism impedes the flow of AC, leading to inductive reactance. The inductive reactance is directly proportional to the frequency of the AC signal and the inductance of the inductor. The formula for inductive reactance is XL equals 2 times pi times F times L, where XL is the inductive reactance in ohms, F is the frequency in Hertz, and L is the inductance in henries. Capacitive reactance and inductive reactance have opposite effects on the phase relationship between voltage and current in an AC circuit. In a purely capacitive circuit, the current leads the voltage by 90 degrees. In a purely inductive circuit, the voltage leads the current by 90 degrees. These phase relationships are important for understanding the behavior of AC circuits containing both capacitors and inductors. In summary, the capacitive reactance of a capacitor is a crucial parameter for analyzing AC circuits. It is inversely proportional to the frequency of the AC signal and the capacitance of the capacitor. The formula XC equals 1 divided by 2 times pi times F times C allows for the calculation of capacitive reactance. Understanding capacitive reactance is essential for circuit design and analysis, particularly in applications involving filtering, energy storage, and signal coupling. The calculated value of 1882 ohms for a 26.5 microfarad capacitor at 400 Hz provides a quantitative measure of the opposition to AC flow offered by the capacitor. This information is valuable for predicting circuit behavior and optimizing circuit performance. Furthermore, the concepts of capacitive reactance and inductive reactance are fundamental to understanding the behavior of AC circuits containing capacitors and inductors.